this meeting here. Okay, so now we are recording. Okay, so section 3.7. First of all, we're going to look at how to solve polynomial inequalities. All right, so let's just try this first one out here. This is going to be a polynomial inequality. And if you were to multiply this out, which we're not going to do, but if you were, this would be what kind of a polynomial inequality?
Second degree.
It looks like it would be a second degree or a quadratic polynomial inequality. Okay. Step number one is we want to make sure we have 0 on one side, and we do. Step number two is to completely factor the non-zero side, which we're fortunate here. It already appears to be completely factored. So life is good here. Now what we're going to do is we're going to find what are called boundary values. And these boundary values are going to be found by setting your factors, your variable factors equal to 0, and then solving your equations. So one boundary value when you solve this equation for x is going to be -7/3. And another boundary value when you solve this equation for x will be +2. All right, so what are these boundary values going to do here? Well, what they're going to do is they're going to take our number line and they're going to partition our number line up into intervals that are going to have to be tested out with our inequality. So this is the real number line. -7/3 is over here, and +2 is going to be to the right of that. All right, so we have 3 different intervals that we need to test out with our polynomial inequality in order to put together the solution set. So interval number 1, interval number 2, interval number 3. I'm going to try to follow the convention that your author is using in your textbook, Liaison, because I know a lot of you do seriously look at the examples in the sections that I cover. And I would strongly recommend that you do so. That can only add to your knowledge as to what's going on. All right. So make sure you do take some time out to look at the examples out in each of the sections that I am going over. Interval number 1. Can you give me something less than -7/3? Now, -7/3 is -2 1/3. Give me something less than -2 1/3.
-3.
And maybe -3. So we'll go with -3. Now, off to the left side here, I'm going to put all the factors of my polynomial inequality here. 3x plus 7 is one factor, and the other factor is x minus 2. Okay. And then here, I'm going to put them together as a product here. This is the convention that's being used in your textbook. All right, so we got a little table here that we're going to have to use to analyze the signs of these factors of this polynomial inequality here. So if we go with -3, is this first factor positive or negative here? If x equals -3, our first factor, 3x plus 7, is going to be 3 times -3 plus 7. I don't really care what number this gives me. I'm more concerned with whether it's positive or negative. And it looks like it's going to be what? Negative. Do you agree? Negative. So this first factor in this first interval is negative. So I'm just going to put a series of negative signs to remind, wait a minute. The first factor is negative. My bad. Fortunately, the second factor also will be negative. Do you agree? Because you put -3 in for x here. -3 minus 2 is -5. So both factors in the first interval are negative. And so therefore, ladies and gentlemen, what would be the product of these two factors? Would it be positive or negative if you multiply 2 negatives together?
Positive.
So therefore, our polynomial inequality is positive for values in the first interval here. Okay. Interval number 2, give me something between -2 1/3 and 2. What's the easiest or nicest value to choose from in this interval?
1.
1 would be okay. 0 would be even easier. Would you agree? 0 would be nicer to work with. You can use 1. I'm going to choose 0. So my first factor, 3x plus 7, will be positive or negative in this interval if I choose 0. What's 3 times 0? 0. And 0 plus 7 is 7, which is what? Positive. So this first factor is positive in the second interval here. There's nothing sacred as to the number of positive or negative signs I'm putting in these intervals. It has nothing to do with anything. I'm just putting a string of them just to remind myself that in interval number 2, this first factor is positive. The second factor would be positive or negative if I choose 0 as a test value.
Negative.
It would be negative. Now, when you take a positive factor and multiply it by a negative factor, our polynomial, which is the product of these factors, will be positive or negative.
Negative.
It's going to be negative in this interval here. Finally, we're going to test out interval number 3 by choosing a convenient test value larger than 2. You know, I'm going to maybe choose 3. If you put 3 into the first factor, is it positive or negative? 3 times 3 is 9. And 9 plus 7 is positive 16. So my first factor is positive in this interval number 3. Let's test out the second factor in this interval. Put 3 in for x. 3 minus 2 is positive 1. Second factor is positive in this interval. And therefore, our polynomial, which is the product of these two factors, will be also positive because a positive times a positive is a positive. So ladies and gentlemen, our solution set's going to be in the interval for which this inequality is valid or true. And notice our polynomial or quadratic polynomial is to be less than 0, which means it has to be what? Negative. So in what intervals is my polynomial inequality negative? That would be interval number what?
1 and 3.
No, in which
Or
our
negative, sorry.
no, in which our
2.
polynomial is negative. Our polynomial is the product of both these factors here. That would just be interval number what? 2. Do you agree? Do we all agree that our polynomial is less than 0 or negative in only interval number 2 here? Would I include the endpoints? Would I include -7/3? Well, if I put -7/3 into this first factor, then the left side is going to go to 0. Is 0 less than 0?
No.
No. You're not going to include -7/3. In a similar fashion, you're not going to include 2, because when x is 2, the left side also goes to 0, and 0 is not less than itself. Bottom line is this: when you have a strict inequality, strictly less than or strictly greater than, you do not include the endpoints of an interval. If you have the less than or equal to or greater than or equal to, then you include the endpoints of the interval. So therefore, I'm going to put a parenthesis, and then I would shade what in between here. And therefore, ladies and gentlemen, you are looking at the graph of the solution set to this polynomial inequality. Any real number that's in between -2 1/3 and 2 would satisfy this inequality or be a solution. Using interval notation, our solution set would be from -7/3 to 2, not including the endpoints. And we're done. Any questions how we solve that polynomial inequality? This is the method that your author is pushing in your textbook too. Any questions, ladies and gentlemen, how we solve that? Okay, maybe we can try another one. Any questions? We got this? Do we all have this accounted for? All right, I'm going to take that as a yes. Okay, let's try this one here. T squared minus 14t is greater than or equal to 49. We want to solve this polynomial inequality. Actually, it's a quadratic inequality because we have a quadratic polynomial, second degree polynomial. What's the first step? Anybody? Do we remember? Well, before we factor.
Move the 49 over to the other
Yeah.
side.
We got to get 0 on one side of these polynomial inequalities always. So let's bring the 49 over to the left by subtracting 49 for both sides. So here we go. So I'm subtracting 49 from both sides, and when I do so, my right side goes to 0. Agree? All right, so that's good. Now we have 0 on one side. So now the next step is to do what? You said
Factor.
we got to try to completely factor this left side. Notice we're up against an easy type of trinomial. Therefore, all I need are two factors of -7 that sum up to -14. Do they, you know what, ladies and gentlemen, I meant this to be a negative, and I do apologize here. I wanted a -49 on the right side. That's an easy fix in your notes. And therefore, this would have to be a what? Not a -49, but a
Positive.
+49. Easy fix in your notes. I do apologize. All right. Now, can we factor this trinomial?
Yes.
Yes.
What two factors of 49 add up to -14?
-7 and -7.
All right, so therefore this trinomial happens to be a perfect square trinomial because it factors into the square of a binomial, namely the square of t minus 7. So now the left side has been completely factored. And that being the case, we can now identify what are called boundary values. Boundary values are values that send your variable factors to a value of 0. And so therefore we would set our factors equal to 0 and solve for t. And notice we have redundancy here because they're the same factor. So we only have one boundary value, namely 7. Taking this boundary value, we're going to partition our real number line up into intervals that need to be tested out. Notice we only have one boundary value, so we only have 2 intervals to test here instead of 3, like the last problem. This is interval number 1, and we'll call this interval number 2. All right, we can make ourselves a little table here. All right. And therefore, I'll put t minus 7 here. I'll put t minus 7 here. And then I'll put the product of t minus 7s, which is our polynomial right there. So in the first interval, give me something less than 7. What would be the nicest value to choose smaller than 7?
0.
0.
Let t be 0 for a test value. Take 0, substitute it into any one of these factors. And 0 minus 7 is -7. So this first factor is negative in the first interval. And it's also, the second factor is also negative in this first interval. And therefore our polynomial will be positive because negative times a negative is a positive. All right. And so therefore our polynomial will be positive in the first interval. Second interval, give me something larger than 7.
8.
If t is 8, then you replace t in one of these factors with 8 and then evaluate. 8 minus 7 is 1, positive 1. So both factors are positive in the second interval. And a positive times a positive renders our polynomial as being positive for values in the second interval. All right, ladies and gentlemen, notice in order to be a solution to my polynomial inequality, all right, I must be choosing numbers or values from the interval in which my polynomial is what? Greater than or equal to 0. And to say that my polynomial must be greater than or equal to 0 is to say that it would have to be what? Not negative, but positive. And we can see that in both intervals, our polynomial is positive. Big question is, would I also include 7 as part of into my solution set? Would I include 7?
No.
Yes, because
Well,
it's greater than or
equal
to 0.
to.
Yeah, because we got the equal sign as part of our inequality, 7 now would be included in the solution set because if you let t be 7, the left side of this will go to 0, and 0, although not greater than itself, is equal to itself. So we would have to include 7. So what do you think the solution set is to this quadratic inequality?
All real numbers.
All real numbers, exactly. It's from literally negative to positive infinity. So to graph this thing, you would be literally displaying the entire real number line. So therefore, in interval notation, your solution set is from negative to positive infinity, and we're done with that problem. There you go. That's your solution set. So all real numbers are solutions to this quadratic inequality. In other words, it doesn't matter what number you put in for t. The left side will always be greater than or equal to 0, always. Okay. Any questions how we did that, that problem there, ladies and gentlemen? So all real numbers are your solutions for that polynomial inequality there. All right, do we have this one accounted for? All right, let's look at one here. We got 5c squared plus 7c is less than 3 times quantity c plus 4. And we want to solve this polynomial inequality. What would be the first move? Anybody? First move here.
Set one side equal to 0.
Yeah, we want to get one side set to 0. That is for sure.
Divide by
Do we
3.
need to factor the 3 in and then move it over?
Yeah, I mean, look, we eventually got to get 0 on one side. That's a no-brainer. But when you do it is kind of like up to you. For instance, you know, subtracting this whole quantity from both sides, that would be perfectly legal. I would maybe be inclined first before we get this thing 0 on one side. I would seriously, I don't know, this is just nagging me on the right side. I mean, I'm just tempted just to distribute this first. So we'll have 5c squared plus 7c is less than 3c plus 12. Now we can zero this thing out by subtracting 3c from both sides and also subtracting 12 from both sides. So here we go. And by doing that, ladies and gentlemen, by subtracting 3c and 12 from both sides, the right side then will indeed go to 0. Cleaning up the left side, simplifying it, combining a couple of like terms. Our polynomial inequality once again appears to be a quadratic inequality. And what's the next move now? What's the next move now?
Factor.
We want to completely factor this left side. Unfortunately, we have a difficult type of trinomial to factor. These require a little bit more work than the easy types. Whether you use grouping on this or whether you use the guess and check or trial and error method, I frankly don't care what method you choose to factor this trinomial. The bottom line is we have to get it factored, ladies and gentlemen. I'm not really going to take the time to show how we factor this unless somebody wants to absolutely see. This is really relegated for intermediate or basic algebra. But when it does factor, we'll factor in the product of two binomials, namely of which we are going to need what? Let's see.
Maybe x, well, not x, but c plus 2 times 5c minus 6.
All right, let's see. C plus 2 times 5c minus 6 certainly looks like it might be promising. We'll have 5c squared negative 6c plus 10c, and negative 6c added to 10c do indeed give you the 4c. Nice job. That would be factored. All right, next move is what? What's the next move in this process? We need to find what we've been calling what?
Boundaries.
Boundaries or boundary values here, which will establish our boundaries. And to do that, we set our variable factors equal to 0 and then solve the equations to determine what those values are. So we would have c is equal to negative 2, and when you solve this equation, you get 6/5. Those are your boundary values. Those values are now going to partition my number line up into intervals that are going to be in need of testing. Okay, so I'll put my number line down here. Negative 2 to the left, and 6/5, which is 1 1/5, will go over here. That is equal to 1 1/5, by the way. So we got interval number 1, 2, and 3 to test out with our polynomial inequality here to form the solution set. Give me something less than negative 2.
Negative 3.
Okay. 5c minus 6. And then we're going to have the now this is not going well at all for me here, this table. All right. If you choose -3 for the first interval, which is something less than -2, the first factor is going to be positive or negative. -3 plus 2 is -1. First factor will be negative in this interval. Second factor is going to be 5 times -3, which is -15, minus 6. That's certainly going to be what? Negative, correct? Our polynomial is the product of these two factors, and a negative times a negative would render our polynomial as being what?
Positive.
Positive in this first interval. I'm going to put that down here. The product of these two terms. I ran out of a little space there, so I'm going to put it below here. So yeah, our polynomial would be positive for values chosen in this first interval. Now the second interval, give me something between -2 and 6/5. Obviously the nicest value is
0.
0. The first factor therefore will be 0 plus 2 or a +2, meaning it's going to be a positive factor. Put 0 in for the second factor. 5 times 0 is 0 minus 6 is -6. Second factor will be negative for values coming out of the second interval. Therefore, our polynomial, which is the product of these two factors, will be a positive times a negative, or will be negative for values chosen from the second interval. Finally, the third interval, give me something bigger than 1 1/5.
3.
Go with 3. So put 3 into the first factor. 3 plus 2 is 5. First factor is positive. Second factor, put 3 in for C. 5 times 3 is 15, and 15 minus 6, I don't care what it is, I know it's positive. Therefore, my polynomial, being a product of these two factors, is a positive times a positive, or a positive in this interval. Now, what interval or intervals is going to constitute our solution set? Well, the intervals that contain our solutions must be intervals for which our polynomial is what? Negative or less than 0. Less than 0 says our polynomial has to be negative. Well, that's only going to occur in what? The middle interval, correct? That's where our polynomial is negative in here. Do I include the endpoints?
No.
No, because we do not have the equal sign as part of our inequality. So therefore, the graph of the solution set is going to have an open parenthesis on -2, closed parenthesis on 6/5, and then we would shade literally in between what? These two values. That would be the graph of the solutions of this quadratic inequality. Interval notationally, the solution set is -2 to 6/5, not including any of the endpoints. Is this making sense here, ladies and gentlemen, so far, how we're solving polynomial inequalities? Polynomial inequalities. These are not polynomial equations. These are polynomial inequalities. Okay. What if I wanted you to solve a polynomial equation? Do we do the same thing that we're doing with this polynomial inequality, or would we do something different? What if I gave you this equation and I said, solve it? I got a question. Did we already solve this equation on here somewhere by having solved this associated inequality?
Yes, by finding the boundary value.
Yeah, I mean, the boundary values, ladies and gentlemen, really are the solutions to this equation. Because we would, if we wanted to solve this quadratic equation, we'd probably want to use the factoring method that we've seen many weeks ago. Set our factors equal to 0, solve for C, and the values we would get are precisely our boundary values that we got or used to solve our inequality. This is how we would solve the equation, correct? We would be done here. But when you're solving a polynomial inequality, you got to use these zeros to partition your number line up into intervals that need to be tested with your inequality. So in solving an inequality, we got to go a little bit further than if we're just solving an equation. Notice the difference, okay? So there is quite a bit of difference in solving polynomial equations versus polynomial inequalities. All right. Let's see, we already tried one like that before. Let's try this one. -1 is greater than or equal to x plus 2 quantities squared. We will try to solve this polynomial inequality here. Now, what would you be tempted to do first here, Liz? I mean, we got to get going on this, and we're staring at it and we're wondering what's the first move. So what do you think the first step is here? What would you do with it? What would you do with it?
Move the 1 over, or
Yeah, you could do that.
change the square into x plus 2 times x plus 2.
And you can do that too. So there's a little bit of initial wiggle room here on this problem. I mean, if you want to, foil this out here first on the right side, you can do that. I think we're gonna have to do that anyways, because we don't have 0 here. Now, if we had 0 here, we would leave this in factored form. We would not multiply this out, but because we don't have 0 over here, we have no choice but to FOIL this out. So you can either FOIL it out now or after you add 1 to both sides. It's up to you. Just whatever you do, whatever move you make, just make sure it's a legal move. X times x is x squared. X times 2 is plus 2x plus another 2x plus 4. Simplifying the right side by combining our middle linear terms, we get this plus 4. What really bothers me with this problem is that I got my x's on the right side of my inequality. I really like my x's over on the left. You think it would be legal to flip this whole inequality statement around? I didn't say just flip the inequality around, the inequality symbol around. I'm talking about flipping the whole statement around. Could we do that and still have an equivalent situation?
Yes.
No problem. Let's bring this x squared plus 4x plus 4 over to the left side. Remember, it's got to be less than or equal to -1. Make sure you have this oriented correctly when you flip the whole statement around. These statements are saying exactly the same thing. Okay. All right. Now to zero this out, I'll add 1 to both sides, add 1 to the right, add 1 to the left. Hence, I have x squared plus 4x plus 5 is less than or equal to 0. And now, ladies and gentlemen, what would be the next move? Of course, we try to do what to the left side? Completely factor the left side. Oh no. Oh no, oh no, oh no. But ladies and gentlemen, what we got going on here is we have what? We have a situation here because we're not able to what? We're not able to factor this left side, are we? I don't know if there's factors of 5 that add up to 4. In fact, there aren't. There are not. So how would we even solve this? I mean, we can't factor this left side. How would we even find our boundary values here?
Quadratic formula.
Quadratic formula? We could. I got a question. Does anybody see something way back at the start of this problem? I'm talking about the initial line of this problem here. Does anybody see anything? Quadratic formula sounds a lot like a lot of work.
Can we split it up with grouping?
Grouping? Well, I don't think this trinomial is factorable because we just can't find, we cannot find any factors of 5 that add up to 4 though. That's the problem. All right. We'll drag ourselves through the mud. Let's drag ourselves through the mud using the quadratic formula. So what's my B? A is 1, B is 2, C is 5. B is 4 rather, C is 5. So we have the opposite of B, the opposite of 4, plus or minus the square root of, I'm using the quadratic formula, B squared minus 4 times A times C, all divided by 2 times A. simplifying this, we're trying to evaluate it. We get 16 minus what? 16 minus 20. You get -4 plus or minus the square root of -4. Oh boy. Do you agree when you have a negative underneath the square root, we bring out I? So this is really, the square root of -4 is really what? 2i, isn't it? The square root of -4 is 2i. Ladies and gentlemen, these are not even real. These are non-real. So it looks like our boundary values are not even real here. So if they're not real, how are we going to partition our real number line up, you know, to test out our inequality? The answer is we're not going to do that. Because our boundary values are non-real, as we would say that we have a contradiction here. We would say that there is no solution to this polynomial inequality. Now, we could have gathered that way back at the beginning, way back up here. Why, ladies and gentlemen, would there be no solution to that polynomial inequality? Why is there no solution to it?
Is it because of the fact that one side of the equation already has a completely factored equation, and then just the general equation is just untrue because it's not equal to 0 or something?
Well, it's not true, because when you square something, when you square a quantity, what do you always get? A positive or negative when you square anything?
Positive.
Positive. Can a positive ever be less than or equal to a -1?
No.
Can a positive ever be equal to -1? No. Could a positive ever be less than -1? No, because that means it would have to be negative itself. Ladies and gentlemen, the right side will never be less than or equal to -1. The right side's always going to be greater than 0. Do you agree? It's always positive. There's no solution. And if you still couldn't see it there, could you see it down here? Maybe, maybe not. But I know we can certainly see it up here. Do you agree? Because the right side is going to be positive. The left side is -1. A positive is never less than or equal to -1. If you still can't see it and you try to go through this whole process here by trying to find some boundary values, the bottom line is if you do not get any real boundary values, then you have to slam on the brakes and just say the polynomial inequality has no solution. So we would say no solution, or we would say the solution set is what? Empty. Okay. So that's your problem with that one. That's your answer for that one there. There is no solution to that one. Okay. So there is no solution for that one there. All right, now I want to go to page in my textbook. Well, let's see here. Let's just scroll down till we get to the homework problems. Okay, we'll look at those when after I now show you how to solve the other type of inequality called a rational inequality. All right, so what I've done here is I've shown you several polynomial inequalities, how to solve them. Okay, how to solve them. Now I'm going to show you how to solve what are called rational inequalities. And you'll see that there's a lot of similarities to solving rational inequalities as opposed to polynomial inequalities. So rational, they're called rational inequalities. The way you solve them is essentially the same way as you solve polynomial inequalities. So there's just some subtle differences. Let's look at this rational inequality. It's called a rational inequality because we have an inequality with a rational expression in it. This is a rational expression. So how would we solve this rational inequality? Well, just like with a polynomial inequality, we had to get what on one side first?
0.
We had to get 0 on one side. We already have that luxury here. Now, the next move is to make sure that both the numerator and denominator on the left side are completely factored, which they are. Being the case, ladies and gentlemen, we're ready to identify what are called boundary values. Boundary values are very similar to what they were for polynomial inequalities. So our boundary values for a rational inequality are going to be the values that send all your variable factors equal to 0 in the denominator and the numerator, the denominator and the numerator. So we take x minus 1 here, set it equal to 0, and we get a boundary value of 1. Take the numerator factor x plus 4, set it equal to 0, solve for x. We get x equals -4 as being another boundary value. Those are your boundary values, 1 and -4. We're now going to take those values and partition our number line up with them. So 1 and 4. And then I'm going to put my factors, x plus 4, x minus 1, and then my rational inequality is the quotient of these two factors here. All right, so again, we'll form ourselves a little table. All right, and we have our intervals that need to be tested out. So we have interval 1, interval 2, and interval 3. All right, so later on, give me some real number less than 1. What would be the next best choice? The easiest choice.
Shouldn't the 4 be a -4?
It should be a -4. What did I have there? Okay, we'll make this a -4. And we'll make this a what? A +1 over here. All right, so this is a +1. Okay. All right, ladies and gentlemen, give me something less than -4, some nice value.
-5.
All right, so if we let x be equal to -5. So if we put -5 into this factor, it becomes positive or negative. What's -5 plus 4? That's a -1. So this factor is negative for values in this interval. Put -5 into this factor. This is -5 minus 1 is -6. This factor is negative for values in this interval. Finally, if you take a negative and divide it by a negative, which is our rational expression, our rational expression will be a negative divided by a negative, which will be positive for values in this interval here. Interval number 2, give me a nice value that is between -4 and 1.
0.
0. If you put 0 into this factor, 0 plus 4, this factor will be positive for values in this interval here. If you put 0 into this factor, 0 minus 1 is -1. This factor will be negative for values in here. Finally, our rational expression will be a positive divided by a negative, which will render it as being negative. Finally, give me something larger than 4, excuse me, larger than 1.
2.
Maybe 2. Put 2 in here. 2 plus 4 is 6. This factor is positive. Evaluate this factor at +2. 2 minus 1 is +1. This factor is positive. Finally, our rational expression will be a positive divided by a positive, which is a positive. And our solution set is going to consist of numbers for which our rational expression is less than or equal to 0, meaning for which it is negative or equal to 0. In what intervals will this rational expression be negative? It'll be right here, the middle interval. Do I include the endpoints? Do I include -4?
Yes.
The answer is yes, because if you let x be -4, our rational expression will become -4 plus 4 over -4 minus 1. which means 0 over -5, which means 0. 0 is less than or equal to itself, ladies and gentlemen. So we do include -4, hence bracket on -4. Do we include 1?
Yes.
Well, if we let x be equal to 1, we'll put 1 into our rational expression. We'll have 1 plus 4 over 1 minus 1, in which case we got 5 divided by 0. But what's 5 divided by 0?
Undefined.
Undefined.
Undefined. And undefined, ladies and gentlemen, is not less than or equal to 0. So we have a big problem when x is equal to 1. So 1 cannot be included in the solution set, hence parenthesis. And then you would shade in between these two, and you're looking at the graph of the solution set to this rational inequality here. Interval notationally, the solution set would be including -4 up to 1, but not including 1. Any questions how we just solved that rational inequality? That's your solution set. So essentially, same song and dance. Got to get 0 on one side, completely factor both numerator and denominators on the left side, set all your variable factors equal to 0 to find both in the numerator and denominator to find boundary values, put the boundary values on the real number line, and test each interval in your inequality to see which intervals will yield solutions. Okay. Any questions, further questions about that one there? All right. Let's just dive into one. Like this. What time is it? Okay, so we'll try this one here. We will try to solve this rational inequality, ladies and gentlemen, for its solutions. To do that, what would be the first move?
Get 0 on one side.
All right, to get 0 on one side, so how are we going to accomplish that algebraically? How do we accomplish that algebraically, ladies and gentlemen? How do I 0 out one side here? How would I move this rational expression over to the left? How do I move this entire rational expression over there to the left?
You multiply it by its inverse.
How
Not inverse, but
about this? Just move this whole term over to the left side. How do we do that?
You just subtract it from that
Minus
side.
1.
Let's just subtract it from both sides. Let's just subtract 1 over x minus 3 from both sides. And when you subtract it from the right side, of course, the right side goes to 0. That's all I did. I subtracted this whole rational expression from both sides, brought it over to the left. Now that we have 0 on one side, we're in business. But ladies and gentlemen, what we really should do is combine these fractions now. We're lucky. We have a common denominator here. And so therefore, 4 over x minus 3 minus 1 over x minus 3 is going to combine to give us 4 minus 1 is what? 3, right? So we'll have 3 over x minus 3. And now we're back to one that looks very familiar based on where we just came from. Notice my numerator is just a constant. Denominator is completely factored. To find boundary values, what do I set equal to 0? Do I set this 3 equal to 0? We don't set 3 equal to 0. 3 is never going to be 0. How about just x minus 3? Only set variable factors equal to 0. So this implies that 3 is a boundary value. That's the only boundary value. So that's going to take our number line and partition it up into some intervals that are going to be in needed testing. So we have 2 intervals that need to be tested, interval 1 and interval number 2. I'm going to put my denominator, and notice my denominator is the only factor of interest here. The numerator is always positive 3. And then I'll put my rational expression, which is this here. All right, give me some nice value that's less than That's less than 3.
0.
Let x be 0. And therefore, if you put 0 into this factor, 0 minus 3 is negative 3. So as it turns out, this factor is negative in the first interval. And what's a positive 3 divided by a negative?
Negative.
Positive 3 divided by a negative is a negative. So our rational expression is negative for values in the first interval. Give me something larger than 3, second interval.
4.
Put 4 into this factor. 4 minus 3 is a positive 1. So this factor x minus 3 is positive in this interval. And therefore, a positive 3 divided by a positive denominator will be a positive. So our rational expression is positive in this interval. Notice to be a solution, our real number that we replace x with has to enable this rational expression to be greater than or equal to 0, which means our rational expression has to be positive or negative?
Positive.
Positive. In which interval is my rational expression positive?
The second one.
Interval number 2. Now, will 3 be included in the solution set?
No.
No. If you let x be equal to 3, your rational expression is going to be 3 over 3 minus 3, which is 3 divided by 0, which is undefined. So therefore, you cannot include 3 in the solution set. Hence, you have a parenthesis, and you'll just shade to the right. You are looking at the graph of all real number solutions to this rational inequality or this original rational inequality. So as long as you choose a real number that's greater than 3, this left side will be always greater than or equal to this right side. Interval notationally, your solution set is from 3 to infinity, not including 3. Questions? How we solve this rational inequality? Is this making sense here? How we solve that rational inequality? Okay. P squared minus 2p minus 8 over p minus 1 is greater than or equal to 0. Solving this rational inequality. Notice we already have 0 on one side, so what would be the next move then?
You factor the top.
Yeah, you want to try to factor the numerator. Fortunately, it's an easy type of trinomial. Are there factors of -8 that add up to -2?
-4 and 2.
-4 and 2. So this numerator top factors into p minus 4 times p plus 2. That's completely factored. Denominator already is factored. Now we can find boundary values. And boundary values are zeros of both the numerator and the denominator. So therefore, we take our factors in the numerator, set them equal to 0, and then solve for p. Likewise, we take our denominator factor, set it equal to 0, solve for p. This equation gives us a boundary value of 4. This one, when you solve for p, gives you -2. And this one gives you +1. So we got 3 boundary values. And as a result, ladies and gentlemen, we're going to take those 3 boundary values and partition our number line up into intervals that will have to be tested. So we got -2, +1, and +4. So we really have 4 intervals we have to test out here, 4 of them. And I'm going to put all of our factors here. You got p minus 4, p plus 2, and then we're going to have p minus 1. And then we're going to have our rational expression, which is to say p minus 4 times p plus 2 divided by p minus 1. Okay. Give me something that's smaller than -2.
-3.
-3, let P be -3. -3 minus 4 has this factor being negative. -3 plus 2, this factor is still negative. And -3 subtract 1 is a negative. Now, what's a negative times a negative divided by a negative? Negative times a negative divided by a negative.
It'd be negative.
It will be a negative. Give me something in between 1 and -2.
0.
All right, let P be 0. So this factor is going to be 0 minus 4 or negative. This factor will be 0 plus 2 or positive. This factor is going to be 0 minus 1 or negative. And our rational expression will be a negative times a positive is a negative divided by a negative. Negative times a positive is negative. And what's a negative divided by a negative?
Positive.
Our rational expression will be positive in this interval. Finally, allow give me something between 1 and 4.
2.
2. If you put 2 in for P, 2 minus 4 is a -2. This first factor is negative. Put 2 in here. 2 plus 2 is positive 4. Second factor is positive. Third factor, if you put 2 in for P, would be positive. So what's our rational expression? What's a negative times a positive? Negative times a negative times a positive would be a what? Negative. And what's a negative divided by a positive?
Negative.
Negative. Finally, give me something greater than 5. Greater than 4, excuse me. How about 5? Put 5 in here. 5 minus 4 is positive 1. This factor is positive in this interval. Put 5 in the second factor. 5 plus 2 is positive 7. This factor is positive. Finally, put 5 in for here. 5 minus 1 is -4. And then our rational expression is going to be a positive times a positive, which is a positive divided by a negative. What's a positive times a positive divided by a negative? It'll be a negative. So what would be our solution set? Well, our solution set has to be numbers for which our rational expression over here is greater than or equal to 0, meaning it has to be positive. Notice it would have to be interval number 2. That's it. Which of these two endpoints do I retain or get rid of? Is -2 supposed to be in my solution set?
Yes.
Yeah, because if you put -2 in here, the numerator goes to 0, but the denominator is not 0.
There's a thing in chat.
Oh, I'm sorry.
The 5 minus 1 is 4.
Hold on.
Yeah, it's not negative.
5 minus 1 isn't negative. Where did I blow that?
The fourth.
Right here. 5 minus 1 is positive. So this should be a positive times a positive divided by a positive is a what? Positive. There we go. Thank you for that chat. So ladies and gentlemen, it has to be these two intervals here. Now, would I include -2? If P is equal to -2, our rational expression will be -2 minus 4 times -2 plus 2 over -2 minus 1. This is going to be -6 times 0 over -3. It'll be 0 divided by -3, which is equal to 0. Is 0 greater than or equal to 0?
Yes.
Yes, we will include -2. Will we include 1?
You wouldn't.
No, you cannot include 1 because the denominator will go to what? 0, correct? Because if P is 1, we're going to have -3 times 3 divided by what? 0. That's undefined. Must not include 1. Shade right here. Would 4 be included?
Yes.
Yeah, if you put 4 in for P everywhere, this factor goes to 0. The numerator would go to 0, but the denominator would still be, positive 3. So 0 divided by 3 is 0. 0 is equal to itself, so we would include 4. And of course, we're going to shade this away. Okay. All right, so that's the graph of your solution set, interval notationally. The solution set would be from -2 to 1, not including 1, in union with including 4 to positive infinity. Agree? Questions how we solve that rational inequality, ladies and gentlemen? Now, you know what? We could have also solved this rational inequality graphically. So rational inequalities can be solved graphically, ladies and gentlemen, but you would have to graph the rational inequality. For instance, let's go to our textbook and let me show you how you could solve some of these inequalities graphically. For problem 55, it says the graph of a rational function is given. Solve the inequality. On what intervals of x would my rational function be less than 0? Well, to be less than 0, ladies and gentlemen, means that the graph for f of x to be less than 0 means our y coordinates would have to be less than 0, which means we're only interested in the part of the graph that is below the x-axis, because to be below the x-axis, points on the graph have to have y coordinates that are less than 0. So on what interval of x would this graph be below the x-axis or less than 0?
2 to 3, not including 2 or 3.
Well, notice the XY axes are in, wait a minute here. No, those are the asymptotes. You are correct. Okay. So it looks like, ladies and gentlemen, on the interval on the x-axis for real numbers that are less than 3, not all less than 3 though, just where? Between 2 and 3, between 2 and 3. So it looks like for x values between 2 and 3, the graph of this rational function is below the x-axis, which means the y coordinates of all these points on the graph that's below the x-axis here would be negative, meaning that f of x would be negative, meaning f of x will be less than 0. So your solution set for part A of this question would be the interval 2 to 3. Notice f of x has to be strictly less than 0, so we would not include 2 and we would not include 3. Why would we not include 3? Why is that obvious?
Because it never touches 3.
That's right, because the rational function is not even defined at x equals 3. Ladies and gentlemen, that's a vertical asymptote. There's no way 3 could be included, okay, in the first polynomial inequality here, the rational inequality, excuse me. All right, so your solution set for A would be the interval from 2 to 3, not including 2 and not including 3. All right. Now, how about B? What if I say this rational function could be less than or equal to 0? On what intervals is that true? Less than or equal to 0?
Including 2.
Yeah, now we
up
would
until
include,
3.
you're right, now we would include 2. Because if you put 2 into this rational function, you do get out 0, because that's an x-intercept. Remember, a 0 is an x-intercept. So you would include 2 up to 3, but not include 3. All right. So for 55A, your solution set would be, maybe I should actually just show you what the solution set should be, because some of you might want to ponder this outside of class. This was a solution set for the first inequality where f of x is strictly less than 0. For B, where f of x is less than or equal to 0, the interval has to be including 2 now up to 3. All right. Now for part C of this question, they want to know on what intervals is our function greater than 0, meaning the graph has to be above the x-axis, meaning the y coordinates must be positive. So on what intervals is the graph above the x-axis?
Negative infinity up to 2, and then above 3 to positive infinity.
That's correct. So from negative infinity up to 2, ladies and gentlemen, on the x-axis, the blue graph is above the x-axis, meaning f of x is greater than 0. Also, it picks up, not including 3 to positive infinity, the graph is also above the x-axis, which means f of x is greater than 0. Notice we cannot include 3 in any of those intervals. And would I include 2? No, because exactly at x equals 2, f of x would be equal to 0, not greater than 0. All right, so therefore, for C, what would be our solution set? It would be from negative infinity up to 2, but not including 2, in union with not including 3 up to positive infinity. That would be the solution set to if f of x was to be strictly greater than 0. Now for part D, what if f of x could be greater than or equal to 0? What would be the only change I would have to make in the solution set from C if f of x could now be equal to 0?
Include 2.
I would have to include 2 now because 2 is a 0 of f of x. It is an x-intercept. So therefore, the answer to D would be including 2 now, bracket. This would be the solution set for f of x greater than or equal to 0. So you can solve these both rational and polynomial inequalities graphically, ladies and gentlemen. You can do so on your graphing calculator. All right. So I just wanted to give you a little snippet there that that's definitely a possibility there. Okay. All right. So that is that there. And let's see, ladies and gentlemen, for classwork number 1, we'll call this classwork number 1. If you can solve this inequality, classwork 1, today is November 3rd. Problem number 1, solve. I'll only give you one problem because we're kind of pressed for time here. I really need to get into solving some variations in the next section. So see if you can kind of like quickly solve that rational inequality. Notice it's pretty much already set up to good to go. You don't have to do any algebraic work initially. So this should go kind of quick. Go ahead. All right, anybody get that solution set?
Yes.
That would be your solution, that would be your solution set, ladies and gentlemen. Because any real number between -6 and 2 will make this rational and equal rational expression greater than or equal to 0 or positive. Right in here. So that'd be your solution set. All righty. So we can call that classwork number 1, okay? All right, I'm gonna have to bring to an end this section 3.6. We have just one other section to tackle, and this will close the door on chapter 3 after we get done with 3.7. So we'll call that classwork number 1. That was just solving a very simple rational inequality. Notice there was no preliminary work necessary. We already had 0 on one side. Everything was already factored and good to go to find your boundary values. Okay. All right. Got that there. Okay. Now the last section in chapter 3 is entitled variations. And ladies and gentlemen, we got 3 different types of variations to consider here. All right. We have what's called a direct variation. Let me give you an example of a direct variation, an real world example. We would say that, like, if you think of a pumpkin, because we just came out of Halloween there, the weight of a pumpkin, ladies and gentlemen, is probably directly varies with the diameter of the pumpkin. Do you agree? The larger the diameter, the greater the weight. Does that seem about right? The larger the diameter of the pumpkin, the greater the weight of the pumpkin. That would be a good example of a direct variation. If the diameter of a pumpkin increases, then the weight of the pumpkin increases. It's called a direct variation. In general, direct variations are going to look like this. Y is going to be equal to K times X, where we would say Y is directly proportional to X, or Y varies directly as X. This is called a direct variation. K is called a variation constant. It's just a number, and it has to be determined by using data or information. Sometimes it's referred to also as the proportionality constant. Okay. Inverse variation is another type of variation that we will tackle. All right. An example of inverse variation. Can somebody give me an example of an inverse variation? 2 variables that are inversely related to each other. Anybody want to give it a stab? Anybody want to give it a try? I showed you 2 variables that are kind of like directly variated or with each other or directly related to each other. Diameter of a pumpkin versus its weight, correct? What if we have an inverse variation? Can you give me an example of a variable that increases and that would cause another variable to decrease? Or vice versa? I'll tell you what, let me give you an example since it's getting kind of chilly outside. How about this one? Ladies and gentlemen, when the air temperature decreases, what happens? What tends to start happening to the heating costs? When the air temperature decreases, heating costs tend to go what? Upward. Do you agree? That's an example of an inverse variation between temperature and heating costs. When one decreases, the other one goes up, and vice versa. All right. Inverse variations look like this in general. Y is equal to our variation constant K divided by the variable X. This is what an inverse variation looks like. Again, K is called your variation constant. It's a number that has to be determined by using experimental data. If we have a combination of direct and inverse variations, ladies and gentlemen, we have what is called a joint variation. A joint variation can be a combination of a direct and inverse variation, but does not necessarily have to be. Generally speaking, though, a joint variation involves more than one independent variable. Notice direct and inverse variations only involve one independent variable x. But with a joint variation, you might have y depending upon many independent variables. This would be an example of a joint variation. We say y varies jointly with x and z. Y varies jointly with x and z. Or another example would be y varies jointly with x and inversely with w. This is called a joint variation. Y varies directly with x and inversely with w. We call these joint variations because we have more than one independent variable. Okay? So direct and inverse variations separately only have one independent variable. We're going to look at these variations and how they can be used to kind of like model real life situations, ladies and gentlemen. Okay. And to do that, why not just go to our textbook and start digging into a couple of very good representative problems here. So we will go to the last section in chapter 3, rather. Oh, let's see. Hold on a second. I got to log in again. I got timed out. All right, so I got timed out there, Liz. Just bear with me for a minute here. Got to go back to the textbook here. All right, here we go. All right, so I'm going to go to section 3.7, and we're going to, go back and try to start working on a couple of problems in 3.7. .7 is entitled Variations. And notice there's a lot of beautiful examples here, ladies and gentlemen, illustrating variations that I would strongly recommend that, you do take some time out just to look through some of these examples and see if you can understand what your author is doing. That's a great way to complement what it is I go over in class. All right, let's just try a couple of problems here. Let's go problems 11 through 20. We'll open up with these. It says for these problems, write models involving direct, inverse, and joint variations. Notice they're not asking us to solve anything yet. They just want us to set up the variation as far as what the mathematical equation looks like, okay? Or they call it a mathematical model. Number 11, it says the circumference C of a circle. The circumference of a circle is the total distance around a circle. It's kind of like its perimeter. The circumference C of a circle varies directly as its radius. How would I, ladies and gentlemen, write that as a variation? Is this an example of a direct or inverse variation, first of all? What do you think?
Direct.
Direct. It says the circumference C varies directly as its radius. So therefore, the equation that would model the situation is we would say C is equal to K times R. You got to have K in your variations because K is called your variation constant. It's the proportionality constant that essentially bridges the two different worlds together of two different variables. So it's important. It's like the interface or the liaison, the go-between, okay? This would be the direct variation between the circumference of a circle and its radius. That would be the answer for number 11. That's called a direct variation. All right, that's an example of a direct variation. So that's indicating that if the radius of a circle increases, its circumference would increase. If the radius of a circle decreases, its circumference would decrease. That's a direct variation between radius and circumference. Everybody see that there? That's number 11. Let's try another one. Let's do number 14. It says the time of travel T is inversely proportional to the rate of travel R. How would we write this variation? First of all, is it an inverse or direct variation? Number 14.
Inverse.
Inverse. So how would we write this? We would say the travel time T is equal to what? T is equal to
K over R.
K over R, you got it. That is how you would model this inverse proportion between travel time and the rate of travel, ladies and gentlemen. That would be your answer for number 14. This is an inverse variation. An inverse variation means that as one variable goes up, like if the travel time increases, the rate of travel would decrease. If the travel time decreases, the rate of travel would increase. There's an inverse variation between these two variables. Okay, that'd be number 14's answer. All right. Try number 16. It says the volume of a rectangular solid. A rectangular solid is is just a fancy word for a box. The volume of a box varies jointly as the length and the width of the box. So how would I write this joint variation? Because it is a joint variation between the volume, the length, and the width. The volume V of a rectangular box varies jointly as the length and the width.
V equals K times L times W.
That is correct. Nowhere do you see the word inversely in here. And because you don't see the word inversely, you would not have any of those variables appearing in any denominator. It just says the volume of a box varies jointly as the length of the box and its width. This would be the mathematical model that models the relationship between, or the interplay between these variables. Okay. So that kind of makes sense. If the length increases on a box and the width increases, obviously the volume of the box is going to increase, and vice versa. That's a direct joint variation between those three variables: volume, length, and width. That one's done. All right, let's see here. Let's try number 19. Actually, we'll try number 20. I want to leave 19 available for you guys for maybe, well, forget it. Let's do 19 because I give you work out of Alex anyways. Number 19, the variable C varies jointly as M and N and inversely as the cube of T. How would we write this as a joint variation? C varies jointly as M and N and inversely as the cube of T.
Would it be C equals K times M times N over T, the square root of T?
Let's see, it says the cube of T.
Oh, sorry, I was looking at
What does the cube of T mean?
T squared, or T cubed, so 3.
T cubed.
The third.
Your answer for number 19 would be this: C varies jointly with M and N and inversely with the cube of T. Notice you have your variation constant K always appearing in these variations. So there you go. What happens to C if T increases? If I hold M and N fixed in value and I increase T, what happens to C? Does it increase or decrease?
Decreases.
If I increase T and hold M and N, and obviously K is a constant, if the numerator is fixed and T increases, C decreases. Exactly. All right. So you see how we're writing these variations here so far? All right. Number 20, we'll try one more. It says the variable D varies jointly as U and V and inversely as the cubed root of T. So we would say D is equal to what? D would be equal to K times U times V over what? The cubed root of T. So the answer to problem number 20 would be this joint variation here. D varies jointly with U and V and inversely with the cubed root of T. Any questions how we're writing these variations, ladies and gentlemen? Let's begin to apply them to actual situations now that we know how to maybe write them a little bit. Let's try number 22 here. It says Now, in these problems says, find the constant of variation K. They want us to actually determine what K's value would be. For number 22, it says, M varies directly as X. When X equals 10, M is equal to 42. Step number 1 for problem 22, we have to write the variation, first of all. So to say M varies directly as X, how do I write that? M varies directly as X. M is equal to what? K times X. M varies directly as X. So first of all, we write the variation. But now they want you to find the value of K. To find K, we're going to need information. We're going to need data. And the data they tell us, ladies and gentlemen, in number 22 is that they say when X is equal to 10, M rather is found to be 42. When X is 10, M is 42. So we can make use of this, substitute 10 in for X and 42 in for M, and then we can solve for K. So 42 is equal to K times 10. Now we can solve for our variation constant. So therefore, K is going to be equal to 42 divided by 10, or K will be equal to 4.2. So therefore, your variation, your direct variation specifically would become M is equal to 4.2 times X now. Everybody see that there? They just wanted you to find K. I stopped right, but I went a little further in showing you what our direct variation would specifically be, having found K. Any questions how we determine K for that direct variation? Just plug the values in where they belong and solve for K. That was one like number 22. All right. Let's see what other one we can do here. We could try number 26. It says N varies jointly as T and P. When T is 2, P is 2.5, N is 15. So to do problem number 26, it says N varies jointly as T and P, so N is equal to K times T times P. So first of all, this would be a joint variation between N, T, and P. Now they want us to determine what K would be. In order to do that, we're going to need to know some numeric values for N, T, and P. Well, they tell us when T equals 2, P is equal to 2.5, N is equal to 15. So now we can use that data or that information to actually solve for K. Pretty simple. Replace T with 2. P takes on the value of 2.5, N takes on the value of 15, and then we can solve for K. So therefore we have 15 is equal to K times 2 times 2.5. And now we just solve for our variation constant or our constant of proportionality K. 15 is equal to 2 times 2.5 is 5. So we got 5K. So what's K going to be equal to?
3.
K would be 3. And we're done with that problem. We have found what K has to be. Okay. And if you want to go further with this problem, therefore your joint variation specifically would have to be N is equal to 5 times T times P, having found K. Is this making sense here, ladies and gentlemen? We're finding the variation constant given data. Okay. All right. Now we can actually start getting into some problems here that have a little bit more going on with them. Let's see here. All right, this looks like a juicy problem. Number 30, no pun intended. I hope you've had something to eat, ladies and gentlemen, because this will make you hungry. I know it made me hungry when I read it first. Number 30, the number of people that a ham can serve varies directly as the weight of the ham. That kind of makes sense. The greater the weight of your ham, the more people you can serve with the ham. An 8-pound ham feeds 20 people. How many people will 10-pound ham serve? Well, ladies and gentlemen, first of all, to answer these questions, we have to set up the variation. Is this a direct variation or inverse variation or joint variation?
Direct.
It looks like a direct variation. It says the number of people a ham can serve varies directly as the weight of the ham. So if I let N be equal to the number of people the ham will serve, and I let W equal to the weight of the ham. Do you agree, ladies and gentlemen? I can set up my direct variation. Number of people we can serve is directly proportional to the weight of the ham. Do you agree? There's my direct variation. But in order to be able to answer these questions, we're going to have to find what K is. We need more information. We got to go back and read this again. Must find K. Oh, it says an 8-pound ham can feed 20 people. There you go. And so, ladies and gentlemen, if the weight of our ham is 8 pounds, we know that we can serve 20 people because that's what they told us. We can now use this data to find W, the variation constant, replacing N with 20, replacing the weight with 8. We can now solve for K. K is going to be equal to 20 divided by 8. And that reduces down by 4 down to 5 halves. And by the way, ladies and gentlemen, what would be the units? What would be the units? I divided the number of people by what? The weight. So the units would be what? People per what?
Per pound.
Per pound. The variation constant is going to be 2.5 or 5 halves people per pound. I'll turn it into a decimal, 2.5 people per pound. That's really the units that would be attached to your variation constant for this particular problem here. Therefore, look at, we can now write our specific direct variation. The number of people we can serve is equal to 2.5 times the weight of our ham. Notice that. Okay. And notice the units, ladies and gentlemen. K's units was what? People per what? Per pound. If you take K's units, people per pound, and multiply it by the weight, which has units a pound, what happens to the pound units? They cross cancel out and leaves us with people. Do you agree? The proper units for N. See how the units work here too? If you got people per pound for units of K times the number of pounds, people per pounds times pounds, the pound units cross cancel out, leaving us with people, the proper units for N. The units have to work out too in the sciences, not just the numbers. All right, let's go back and answer the question now that we've developed our specific direct variation here. I don't know if we're gonna have time to do all these problems, but let's just try to do maybe at least A here and D. How many people will a 10-pound ham serve? So ladies and gentlemen, if I have a 10-pound ham, how many people can we serve? Well, we use our direct variation we formed. So the number of people we can serve with a 10-pound ham is going to be equal to 2.5. Technically, it's people per pound times 10 pounds. 2.5 times 10 is 25. The pound units cross cancel out, leaving you with people. We can serve 25 people. There you go. You can serve 25 people with a 10-pound ham. Does that make sense? 25 people with a 10-pound ham. That would be the answer for 38. The other ones work the same way. How many people will you be able to serve with a 15-pound ham? Well, if I have a 15-pound ham, how many people can I serve? If the weight is 15 pounds, I'll be able to serve 2.5 times 15, which is, what's 2.5 times 15? Oh, is that 37.5?
I think so.
37.5 people. Yeah, what's a half of a person? You know what I'm saying? Is that a person that's half in your door and half out your door? Why not just round it up and say you can serve at least what? At least how many whole people?
37.
37 people, and you're gonna have a little bit left over for maybe a snack later on. All righty? 37 people, ladies and gentlemen, can be served with a 15-pound ham according to this direct variation between number of people served versus weight of ham. Last question, D. Notice they're having us turn things around now. It says if a ham can feed 30 people, what would be the weight of the ham? Now N would be equal to 30 because we can serve 30 people. They want to know, they want us to find out what weight ham would be able to serve 30 people. Now we know N is 30. So using our variation up here, we let N be 30. And now we have to solve for the weight of the ham, just the opposite. How do we solve for W? Divide 30 by 2.5, get on your calculator and dial that up. And what do you get?
Well,
You get 12. So we would need a 12-pound ham to serve 30 people. Do you agree? We've answered that question. You need a 12-pound ham to serve 30 people. Did that problem make sense there? First, we had the recap. First, we declared our variables. Then we set up our direct variation, the skeletal form of it. We then used data they gave us to find K. Once we found K, we then established our specific direct variation. And then from there, we were able to answer specific questions using that specific direct variation. All righty. That's how you're going to do most of these problems in this section. They work essentially the same way. Let's see here. It's 10 after 4. Let's see if there's another one here. Oh, let's see. Well, let's see. I don't know if we got any electricians in here. Any electricians in this class? That was my fear. Let's look at number 35. The stopping distance of a car is directly proportional to the square of the speed of the car. Let's stop right there and see if we can write this variation for number 35. Let's at least try to set up the skeletal form of the equation. I'm going to let D be equal to the stopping distance, ladies and gentlemen. I got to define some variables here. So suppose D is the distance a vehicle needs to stop, however many feet, to come to a complete stop. The speed of the car, I'm going to let V be the velocity of the car. Velocity and speed, same thing for our purposes here. Okay. So it says that the stopping distance is directly proportional to the square of the velocity or square of the speed. How do I write that as an equation? The stopping distance, the distance a car needs to stop, is directly proportional to the square of the velocity or the speed of the car. So D is equal to what?
K times V squared.
K times V squared. That models this situation. Distance the car needs to stop versus how fast the car is going initially at the time you slam on the brakes. Okay. All right. We have to find the variation constant K. We need data. And so what they did is they probably went out in the field and tried a car on a dry road. Had to go in at a certain speed and told the person to slam on the brakes, and then he measured the length of the skid marks, ladies and gentlemen. You could actually do this out in the field, collect your data. And so what they did is they found that if a car traveling 50 miles per hour has a stopping distance of 170 feet, stop right there. So therefore, suppose a car's velocity is 50 miles per hour, and then they slam on the brakes, and the distance to stop they actually measured was 170 feet. We can now find our variation constant. Do you agree? Because we have data that was actually collected and out there in the real world. So ladies, I'm going to help me solve for K. I replaced the distance with 170 feet. I set that equal to K times the velocity squared. So this is 50 miles per hour, squared, correct? Now the units aren't going to have much meaning in our mind, but this is what we got. So to solve for K, we're going to divide 170 by 50 squared. Does anybody want to get on the calculator and dial that up?
It's 2,500.
Okay, so we have 170 divided by 2,500. Now what's 170 divided by 2,500? Can you tell me what that is? That's going to be kind of a small number. It's a decimal, correct?
Yeah, it would be 0.068.
0.068? All right, did you actually round off a little bit, or?
That was the exact number that came out.
Oh, that is exact, 0.068. Well, how nice is that? All right, 0.068. And if you wanted to put the units in here, you would have feet per miles per hour squared. Now, I know that looks strange, these units, ladies and gentlemen, but that would be the technical units attached to your variation constant. Feet divided by miles per hour squared, okay? All right, let's go back, and so therefore our direct variation becomes a little bit more specific now. D is equal to the 0.068 times V squared. Now we can answer some questions now that we developed our direct variation between stopping distance and velocity of the vehicle. It says, find the stopping distance of a car that is traveling 70 miles per hour. And so, ladies and gentlemen, if the speed or a velocity of a car is 70 miles per hour, they want you to compute the stopping distance. Simple. Just replace V with 70. So therefore, the stopping distance is going to be 0.068 times 70. And we have to square that. Can you get on your calculator and dial this up? And tell me what the stopping distance would be in feet.
333.2.
330.2.
33.2.
33.2.
Yeah. Like 333.2, sorry.
Okay, I was going to say. So the stopping distance is 333.2 feet.
Yes.
All right. A football field from goal line to goal line is 100 yards. 100 yards is 300 feet. Ladies and gentlemen, this is hard to believe, but if you're going 70 miles per hour down the road and you slam on your brakes, you would need the length of a football field to come to a complete stop. The length of a football field, goal line to goal line, and then some to stop, at least on this surface in which the experiment was conducted. Okay. All right, as far as these units are concerned, if you take K's units, which are feet per mile per hour squared, and if you multiply it by the velocity squared, which is miles per hour squared, what happens to mile per hour square units? They cancel, leaving you with what units? Feet. And those are the proper units for what? Stopping distance. Do you agree? So you see how the units work out too in these variations? I've been leaving the units out for the sake of brevity, but the units have to work out just as nicely as anything else. Okay. All right. So solving some variations. All right, let's see here. Now it says for B, if it takes 244.8 feet for a car to stop, how fast was it traveling before the brakes were applied? Ladies and gentlemen, they can actually determine the speed with which a vehicle was going if it goes into a skid and leaves skid marks on the road. They can measure the length of the skid marks, and they have a mathematical model that's used based on whether the road is dry or wet or snow covered or ice covered. They can model the speed with which you were traveling when you slammed on the brakes. They actually use that out in the real world. Police officers use that. Engineers develop the model, and police officers use it to determine your probable speed, and then they can use that in a court of law. Okay, so if it takes 44.8 feet to stop a car, how fast was it traveling according to our model that we developed? 244.8 feet to stop. That means the stopping distance was 244.8 feet. They want to know what your velocity was at the time when you slammed on your brakes. All we got to do is use our model to determine that. Replace D, the stopping distance was 244.8. Set that equal to 0.068 times your velocity squared. And now we just solve for the velocity. Divide both sides by 244.8. Divide both sides by 0.068, excuse me. And then take the what of both sides. How do we solve for V? take the square root of both sides. So ladies and gentlemen, get on your calculator and dial this up and tell me what your velocity was, your approximate velocity when you applied the brakes. If your skid marks were 244.8 feet in length on the pavement, how fast were you going? We're assuming the road conditions are the same in this situation that were used to build this particular variation.
I got 3,600.
3,600
Or-
miles per hour?
I forgot to square root it, sorry.
Yeah, take the square root of it. That don't sound reasonable. Again, the key assumption is that the road conditions are the same in this situation for this particular
60.
incident as they were in order to build this model. We're assuming that. What
V
speed
equals
about?
60.
60 miles per hour? Okay, so approximately you're traveling about 60 miles per hour to leave the skid marks of this length on the pavement. Okay, so variations, ladies and gentlemen, can actually be used to model various situations in the real world. This is just one example. They probably have a mathematical equation for different types of road surfaces for like wet roads, dry roads, snow-covered roads, whether the road is a gravel road or a blacktop road. Okay, they develop these mathematical models in the lab, and then they can apply them out in actual accident scenes to predict the approximate velocity the vehicle was traveling. And that can hold up in a court of law because that's the scientific data, scientifically designed mathematical models based on data. So mathematics can actually go to court too, ladies and gentlemen. It can actually go to court. All right, so variations, ladies and gentlemen, variations, whether they're direct, inverse, or joint, is the order of business of section 3.7. And I think that's good enough for today. I was going to give you one last class problem, but we're out of time here. And so I will post the chapter 3 quiz and get you going on that. I did update the homework in the rest of chapter 3 on Alex. I would probably do the homework first. Seriously, I would do the homework first and then do the quiz and then do the exam. I would do it in that order. So please, even before doing the homework, you might want to look at some examples in the sections, then do the homework, then do the quiz, then do the exam. I would do it in that order. I think by doing that, you'll have the best chance at maximizing your grades on the quiz and the exam. All right. Okay, so ladies and gentlemen, I'm gonna have to let you go here, and you have a great weekend. I'll stay on the line if there's any other questions or concerns here, and be looking for my email for the due date on that exam. All right, take care.